So it's my pleasure to talk to you today about some statistical ideas and concepts that are often, let's say, difficult to remember if you don't use them a lot, right? And so statistics is really pretty easy, but hopefully today we can cut away through some of the nebulousness around these topics so that when you come to these questions on your board exams, you dial them in and those are easy points for you rather than just skipping on and hoping that you get enough in other areas. All right, so we'll talk about some terms that are, I think, important to understand but easily confused. Things like sensitivity, specificity, positive and negative predictive values. My goodness, those are so easy to interchange. And how do we identify which is which and how do we compute them in a very short period of time? We'll talk about all of that. We'll also look at study designs and strengths and weaknesses associated with specific types of study designs that you may encounter on these board exams. P-values, what on earth is that? What is a real definition for a p-value? I'm sure many of you have encountered these before, but how do you define that? Where does it come from? Understanding things like that I think would be important to you, as well as confidence intervals, and then we'll follow up with things like number needed to treat. All right, so let's get started here. The way that I evaluate a diagnostic or screening test is with a couple of measures, right? So if I've got a good diagnostic test and I have a whole bunch of people that I know have the condition or the disease that I'm testing for, and I give them that diagnostic test, if it's any good, it should turn up positive a whole bunch of times, right? So I've got people that I know have the disease, I give them the test, and I see how many times the test comes up positive. We call that the sensitivity of the test, right? So in statistical language, I might say the probability of a positive test given the disease. So this little vertical line is a condition. And that condition is important. I know these people have the disease. So I've developed my own diagnostic test, and it has 100% sensitivity. It's very inexpensive. It's easy to deploy. I can take it anywhere in the world. And what happens is when somebody comes in and wants to be evaluated for any condition, I run them into my diagnostic test center, and it immediately tells them that they have the disease. They have that condition. What's the sensitivity of that test going to be? It's not going to miss a single person that actually has the disease, but is that a very good diagnostic test? So the sensitivity is only part of the picture, right? What's the other piece of the puzzle that we need to evaluate a diagnostic test? The specificity. So the specificity is now I take a whole bunch of people that I know don't have the disease, and I give them my diagnostic test, and I see how many times that turns up negative. And if my diagnostic test is good, it will turn up negative a large proportion of the time. Okay, so in statistical language, I may say the probability of a negative test given they don't have the disease. This little line above there stands for the complement or the opposite of the disease. Right? So people that have the disease, probability of a positive test. People that don't have the disease, the probability of a negative test, sensitivity and specificity. Okay, so let me set the stage for another scenario. Suppose a random person comes into your clinic and wants to be tested for a particular disease. You give them the diagnostic test and it comes up positive. Potentially, their next question is, what's the probability I have the disease given the positive test result? Notice that with the sensitivity, I have the probability of a positive test given the disease. This latter situation is I have a positive, I'm interested in the probability of the disease given a positive test result. That's different. What do we call that? It's the positive predictive value. So the positive predictive value is simply the probability that the subject has the disease given a positive test result. Now with this person, I don't know their disease status. All I know is their test result. right? And that's different than the sensitivity. In fact, it can be very different than the sensitivity. There are very good diagnostic tests for things like AIDS with high sensitivity and high specificity, but the prevalence is pretty low. And so even with a positive test result, the probability they have the disease can still be kind of small. Right? So distinguishing between those items is important. Likewise, we can get a negative predictive value, the probability of not having the disease given a negative test. Right? So we'll talk about how we compute all of these, but I think it's worth defining them so we keep them in their own little spheres and distinguish between the four of these items. So when you encounter a question about sensitivity, specificity, PPV, NPV on your board exams, I would recommend constructing a small table. And in this table, what you'll have are the true disease stata for these columns. So whatever the gold standard is for evaluating whether or not they have the disease, maybe it's a certain type of culture, or maybe it's a pathology report. The true disease status as the columns. And then the test result from your diagnostic or screening test as the rows. So I have disease positive, disease negative, and then I have the results of my diagnostic test, test positive or test negative. And then it becomes very easy. It's just simply filling in this table. So if I have folks that are disease positive and my diagnostic test turns up positive, that's a true positive. Okay, it made the correct assignment. Those that had test negative are false negatives. They really had the disease, but the test said that they didn't. And then the total is just the sum of those two things. So thinking about computing, say, the sensitivity and specificity, remember the sensitivity is among people that we know their disease status. They have the disease. So this column really pertains to the sensitivity of the test. This is the total number of people we know have the disease. And this is the number of times that it turned up positive. So this divided by the total becomes the sensitivity of the test. So once you fill in a table like this, it becomes very easy. I just focus on the columns for sensitivity and specificity. If I move over to this disease negative column, if it turned up positive for those that I know don't have the disease, that's a false positive. If it turns up negative for those that I know don't have the disease, that's a true negative. And the sum of the two gives me the total number of disease negative subjects. So now I have those people that I know don't have the disease. Here's the total number of true negatives, and I can compute the sensitivity. Specificity. All right, what about the positive predictive value and negative predictive value? Well, it's very easy. We transition from looking at columns to now looking at the rows. So if I take the true positives divided by the true positives plus the false positives, that actually gives me my specificity. Likewise, I'm saying the wrong thing, my positive predictive value, thank you. And if I look at this test negative row and take the true negatives divided by the true negatives plus the false negatives, that gives me my negative predictive value. So looking at these formulas makes digesting that information from a table very easy. Right? Now I want to point out that the positive predictive value, negative predictive values are actually very simplified formulas for computing those. It assumes that the prevalence of the disease is actually 50%. And you get some cancellation in the more complicated formulas that reduces to this. The prevalence of the disease plays a major role in the positive and negative predictive values. Right? So we'll talk about that. If the prevalence of the disease is really small, then that positive predictive value may actually end up being pretty small. Even if we observed a positive test result, low prevalence means positive predictive value can still be small. The negative predictive value gets boosted. Okay, we can say if we had a negative test result, we can be pretty sure that that's a true negative. But the positive predictive value, we can't quite dial that in, and we want to do some follow-up investigation on that. All right, so let's see how much we've learned here. In a study of 2271 patients with a history of colon cancer, fecal occult blood testing is done to screen for recurrent colon cancer. 146 patients have positive FOBT, 2125 have negative FOBT. Colonoscopy, so that's the gold standard in this case, is done on all the patients, finding 46 cancers, 12 patients with positive FOBT have colon cancer, and 34 with negative tests have colon cancer. Oh my heavens, there's so much information in there. Just make yourself a little 2x2 table, gold standard, positive, negative, test results on the rows, and all of that information will just sort of fall into place for you. All right, take a second to answer that one. Ooh, that's not even fair. 10 seconds to answer that question. Wow, look at that. Good job. About 25%, about a fourth. So this particular test is not that sensitive, right? So let's take a look at how we might compute that. There's my table. There's the information that's given to me in the setup of the story problem. Right? And like any story problem, you just need to pull out the important pieces of information and arrange them in a meaningful way. So I have 46 cancer positive subjects here. 12 of them were identified by the diagnostic test. So my 12 divided by 46 gives me the sensitivity of the test. Right? And that turns out to be my 26.1%. The rest of the information from that table can be filled in. So if I were asked additional items like what's the specificity of that test, well, I just switch over to this row and I take the 2091 over 2225 and get 94% specificity. So this test is really good about ruling out this cancer in subjects, but not very good about ruling in. Positive predictive value then, looking at the rows, I can take my test positives divided by the total number of my true positives divided by the total number of test positives and get my 8.2%. And likewise take my true negatives divided by the total number of negative tests to get the negative predictive value. All right, so you guys feeling good about those questions? You guys going to dial those in on your board exam? Sensitivity, specificity, PPV, NPV, no problem. Make yourself a table and you got it. Okay, let's talk about study designs and in particular aspects of these study designs that you may see on your board exams. We'll start with some of the weakest type of studies and slowly progress through stronger and stronger studies. All right, so a cross-sectional study is typically viewed as one of the weakest type of study designs. This really just takes a group of people at one time point and looks to see if they have the risk factor that you're interested in studying and the particular outcome of interest. And so the difficulty with this is it's very hard to say which came first. So we can't typically draw conclusions about cause and effect from these types of studies. At most, we can make statements about weak associations that are observed. And some of the difficulties with these types of designs is there are a host of what we call confounding factors. Things maybe in a patient's history that may be related to the risk factor as well as the outcome that we haven't measured or that we haven't accounted for. Right? So these cross-sectional studies don't deal with those very, very adequately. So these are rarely done in clinical trials where we're trying to really find the effect of a certain treatment or a certain risk factor on a particular outcome. An example of this might be a researcher interested in the question, is numeracy, or a person's ability to understand and comprehend numbers, associated with their perceived risk of breast cancer? So you ask somebody, what's your risk of breast cancer? And you may get a whole bunch of different responses. And then you may ask them to do a little bit of math and figure out what their level of numeracy is. And is their accuracy in that perceived risk of breast cancer related to their ability to comprehend numbers? So that might be a question of interest. So we may give this survey to women presenting in the clinic for mammogram along with a 10-question math quiz. And their perceived and actual risk of breast cancer may be obtained. So we'll ask them a host of questions about their history, about their age, things that will give us a good feel for their actual risk of breast cancer. And we will see what's the difference between their perceived risk and their actual risk. Was that small or was it large? Now, what was their answer? What was their score on that 10-question math quiz? Was it a high score or a low score? So suppose if those with lower quiz scores have significantly lower accuracy, what can we conclude about that? Well, we can conclude that we observed an association, but we can't make statements about what caused what, right? There's actually very little that we've controlled for in this particular study, and there may be several other things that affect both their numeracy and their perceived risk of breast cancer. So very weak statements to be made from these types of studies. But they're not very expensive. They're easy to do, and so they get done a lot, actually. Not necessarily as clinical trials, but as research topics. And so it's not uncommon to come across these. They're actually quite frequent. Okay, a stronger type of study is what we call a case control study. And this is more of a retrospective type of study where we may take people that we know have the condition of interest and match them up with some folks that don't have the condition of interest but are similar in other ways to the cases. These are going to be our controls. And an example of this might be where we take current Alzheimer's and non-Alzheimer's patients. These have Alzheimer's, these don't have Alzheimer's, and then we look back in their history and we say, what did you guys have in common? Or what did you not have in common? In particular, this study may deal with coffee consumption. Were those that have Alzheimer's more likely to drink coffee earlier on? That may be a question or an association that we want to tease out of this type of study. The trouble with this is there could be lots of confounders as well. We're not really controlling for different questions that may be also associated with Alzheimer's. We can't necessarily randomize people to different treatment groups or different types of exposures to see how that affects their outcome of Alzheimer's. We're really just stuck with observing what happened in the past. So these are stronger than cross-sectional studies, but also somewhat weak in the fact that they only provide association type information and not cause and effect. Again, we don't know necessarily that causal pathway in these types of studies. Now, an interesting thing from case controls is the type of measure that we get out of there. And this will come up again when we talk about hypothesis testing and confidence intervals, in particular relating to questions about confidence intervals on your board exams. Case control studies yield measures called odds ratio. We usually call that just an OR, an odds ratio. And what on earth is an odds ratio? Okay, well, it's a ratio of odds So we need to know what odds are. And odds by themselves are ratios. So an odds ratio is a ratio of ratios. If this isn't getting confusing, then you're better at math than I am. So let's just take a step through each of these things, okay? Let's look at an odds. An odds is defined as the success probability, what I'll call pi here, divided by 1 minus pi. What might be another term for that? If pi is the success probability, 1 minus pi could be the failure probability. Good. Yeah, so it's just the probability of success over the probability of failure. That's the odds. And so I might have the odds for a control group, and I might have the odds for a treatment group. And I want to know how those odds relate to each other. Is the success to failure ratio for the treatment group the same as the success to failure ratio for the control group? If it is, that tells me something about the risk for that group. Okay, so my odds ratio then constructs that comparison. So I'll have the odds for the cases over the odds of the controls. Splitting that out further just gives me the probability of success for the cases to the failure of the cases, probability of success to the controls over the probability of failure to the controls. Notice that the odds ratio itself is not giving me a direct comparison of the success probabilities for the controls to the cases. We'll talk about that in a moment. But the odds ratio is a little different than that comparison, so it has a bit of a different interpretation. I don't associate things like likelihood or there's a 50% greater chance that the cases have this particular risk factor than the controls. All we know is the magnitude of those odds. Okay, so it's important to note some of these differences between odds ratios and other types of ratios we might encounter. So an odds ratio of 1 means that there's no difference in those odds. Success to failure ratio for the controls is the same to the success to failure ratio of the cases. If the odds ratio is greater than 1, then this value, the odds in the numerator, were larger than the value in the denominator. So the success to failure ratio for the cases is larger than the success to failure ratio in the controls. Likewise, odds ratio less than 1 means the odds were greater for the controls than they were for the cases. So there's this interesting number of 1 that keeps showing up when we talk about comparing ratios. We'll see it again when we investigate another type of study. But file this away. Under your odds ratio file, think about the number 1, and we'll come back to that in a minute. 1 indicating that there's no difference between those groups. Okay, so a cohort study is a stronger type of study than the case versus control. Notice that as we progress in these types of studies, they become a little more difficult, time-consuming, and expensive to implement, but they're stronger and we can make stronger statements about them. A cohort study is usually prospective. So I'll take a group of people at a certain point in time, and I will follow them for a period of time and see what develops. See if the outcome of interest happens. And maybe I choose these people in a careful way so that I have coffee drinkers and non-coffee drinkers. And then I follow them to see which of them develop Alzheimer's. This is going to be viewed as a stronger type of study than our case control. More likely to show that cause and effect relationship. I can see which one happened first and maybe make some arguments about what was likely to cause the other. Now with cohort studies, we get a very nice measure out of here rather than sort of this nebulous odds ratio. I can get what is known as the relative risk. This compares the disease of in subjects with the risk factor to the subjects without the risk factor. And the relative risk is simply the probability of success, the probability success kind of loosely defined. Maybe success in some cases is the prevalence of cancer or obtaining Alzheimer's disease. So the probability of success in the cases over the probability of success in the controls. This kind of measure we can put probabilistic statements on, like there's a 50% greater chance of developing Alzheimer's among coffee drinkers than not. With the relative risk, we can say things like that. With the odds ratio, we have to be more guarded in those interpretations. So likewise, a risk ratio of 1 means what? Probability of success for the two groups is the same. Relative risk greater than 1 means the risk of the disease is greater for subjects with the risk factor. Relative risk less than 1 means the risk of the disease is greater for subjects without the risk factor. And it really just depends on what I have in the numerator and denominator, right? If I flip those, I'm sophisticated enough that I can figure out what that relative risk means if it's greater than 1 or less than 1 by changing what's in the numerator and denominator. Right? So just knowing what's in the numerator, what's in the denominator, that can help you identify or interpret that relative risk. So again, we see this value of 1 when the groups are the same. Okay, file that away. We'll come back to that a little bit later. Randomized controlled trials. These are like the strongest type of studies we can do. These are typically prospective, so as subjects come in, we have 2 treatments, a control and a treatment. And we want to randomly assign subjects as they come into these 2 different treatments. And you may be asking yourself, well, what's the difference between that and a prospective study where if I randomly assign them to these 2 different treatments and then follow them over time, what is the distinction? The important difference is in the cohort study, we're not randomly assigning them to, say, coffee drinkers and not coffee drinkers. That could be an interesting study, but that's probably unethical. In the randomized controlled study, we are making those randomizations. So that immediately gives rise to questions about when is a randomized controlled trial feasible? So unfortunately, looking at things like the effect of tobacco use is probably not ethical to randomize people to smoking and non-smoking groups. So these are really nice, strong studies, but they have limitations. And some of them have ethical limitations. And that randomization process, what it does is it takes all of these other lifestyle, environmental variables that these people may have encountered that we don't even know about, and it sort of averages those effects out. And if I take a randomized trial that's large enough, all of those background variables and effects are averaged out in such a way that the difference between the groups now is due just to the treatment rather than other types of exposures or confounding variables. So this randomized trial really deals with confounding variables in a nice way. We talk about blinding in these types of studies. So the patient may be blinded and not know which arm of the study they're assigned to, whether it's the treatment or whether it's the control. And that's helpful because there are things like adherence issues when patients know that they're no longer on the treatment arm. Like, I'm taking a sugar pill, that's not going to be helpful, and then they stop adhering, things like that. So blinding in these types of studies is important. If the patient is blinded and the person administering or recording the data from these patients is also blinded as to which treatment they received. We call that double-blinded. Right? And these are aimed at reducing bias in the study. An example of this might be when we give an ACE inhibitor or placebo to diabetes mellitus patients and see if those given the ACE inhibitor have less risk of developing renal insufficiency. And we might randomize them at the beginning of the study, follow them over a certain period of time, and see what develops among those two different groups. Another interesting type of study is what we might call a meta-analysis. And in my mind, a meta-analysis is a really slick way of having other people do your work for you. Right? So you actually just go out and you gather studies that have already been done, and you create sort of this composite description of what happened. Right? So it combines the results of several studies focused on the same topic. Really nice things about meta-analyses are that they combine various studies and give you a weighted average of those conclusions. So maybe several studies point to one association, and you have a couple similar studies that point the opposite way. And you want to combine all of those results into sort of an overall statement about that association. Well, you can use a meta-analysis to do that. And it's also very inexpensive. Like I said, other people are doing this work for you, so it's not very time consuming, and you just have to track down these papers. Some of the weaknesses, however, are that the studies are done at different locations at different time points and may not share a lot of the same characteristics. Maybe in one study they used a particular disease definition, and in another study they used a different disease definition. Perhaps the inclusion-exclusion criteria are slightly different. Maybe the ages of some of the subjects are different. And so that makes it a little bit challenging to really compare apples to apples. Okay, so reviewing charts of hospital admissions reveals 21 children with a particular disease. Carefully matching ages, genders, and ethnicities of these subjects, 42 similar subjects without the disease, so we picked out 2 for each person that had the disease, are identified. Comparisons of potential risk factors are made between both groups. What type of study design is this? Cross-sectional, case control, cohort, randomized clinical trial, or is this a meta-analysis? Yeah, very good. So this is our classic case control. We start off with the folks that we know have the condition of interest, and we pick out some matches that don't have that condition of interest but are similar to them in things like age and race and gender. And then we try to figure out why they differ in terms of that particular condition. Okay, so cross-sectional would be more of just taking everybody that we observed during a certain time period and trying to look for associations between a risk factor and a particular outcome. So that's why this isn't a cross-sectional study. We actually just pick out those 21 patients with the disease. Should also point out that these case control studies are not useful for trying to estimate things like the prevalence of a disease or these 21 subjects that we found with the condition. We really, our total sample size here, almost a fourth of them are going to have the condition of interest. And that the prevalence of that disease in the population at large may be a lot smaller than that. Okay, so we can't use case control studies to estimate things like prevalence. Okay, here's another one. This is actually a real study. In 1948, 5,209 subjects were enrolled in a study to determine the risk of developing cardiovascular disease. Anybody know what study this was? And this continues on today. So we have like grandchildren of these people enrolled in this Framingham Heart Study. Subjects were extensively evaluated for physical and lifestyle characteristics at enrollment. Enrolled subjects were disease-free at enrollment and then evaluated every 2 years for 30 years for the presence of cardiovascular disease. What type of study is this? Cross-sectional, case control, cohort, RCT, or meta-analysis? Wow, you guys dialed that in. So the cohort studies are actually fairly easy to identify, right? We don't have a randomization process happening, and we're starting at a certain time point and following subjects over time. Right? So good work. Okay, hypothesis testing. Oh my heavens. How many of you have heard of null and alternative hypotheses at some point in your lives? Yeah, okay, so my goodness. So why don't we take a moment, take a deep breath, and we'll actually cut away some of the fog around these ideas and get them solidified in such a way that you understand hypothesis testing at a very high level. Anytime you do a statistical test, you are comparing two competing hypotheses. And those are the hypotheses that we just named, the null and alternative hypotheses. They are always lurking in the background of any statistical test. So if you see a p-value, there was a hypothesis test done. So it's a good idea for us to understand what's happening with these hypothesis tests. I put superiority test in here because often we're interested in testing to see if maybe treatment A is better than treatment B. Right? So we'll kind of focus on that. I'll develop my null and alternative hypotheses around a typical type of study. So the null hypothesis, often denoted with this H naught, H sub 0. In a superiority test, to see if two treatments are the same or if treatment A is better than treatment B, the null hypothesis assumes that those two treatments are the same. And the alternative will assume that the treatments are unequal. This alternative hypothesis actually has many names. Sometimes you'll hear it called a research hypothesis. That's because whatever you're trying to establish with your study has to be stated as the alternative hypothesis. We'll come back to this a couple of times, but I don't think I can emphasize it enough. We can never prove statements that are placed in the null hypothesis. The philosophical foundation of hypothesis testing uses proof by contradiction. And so whatever is stated in the null says that it can be disproved, but it can never be established. It can never be proven. Right? So whatever, if you're looking at a study or conducting a study of your own, whatever you want to establish needs to be stated as the alternative. So we'll denote that as H sub A. You guys still with me so far? All right. Then we'll move forward. So we'll collect some data after formulating the null and alternative hypothesis, and we'll reject the null hypothesis in favor of the alternative only if there is strong evidence against the null hypothesis. So if my null hypothesis, think about two treatment means. Okay, maybe I'm looking at maybe measures of pain tolerance for treatment A and treatment B. And the null hypothesis says, on average, those two things are the same. So I collect some data, and what I see is that treatment A actually has a little higher score than, say, treatment B. Okay, that's the process we're talking about here. We're collecting data. My null hypothesis is still sitting here saying these two things are the same. Now I observe some data and I say, well, the data that I collected says otherwise. If it's far enough away, then I'm going to reject the null hypothesis that says those means are the same. So I have to get far enough away. This much away is not going to let me reject the null hypothesis. This much away, maybe that's going to let me reject the null hypothesis. And the whole point of statistics is that gives us a measuring stick for how far away we need to be before we can say, okay, those things are different. That's enough evidence against the null hypothesis that we're going to conclude the treatments are not the same. And then the conclusions that we have about hypothesis testing. Okay, if just establishing the null and alternative isn't weird enough, the conclusions that we make are we either reject the null hypothesis or we fail to reject the null hypothesis. Who talks like that? Okay. We don't use words like that, right? What we want to say is accept the null hypothesis, but we can't. We have to be very careful about this language, right? We either reject the null hypothesis or we say, we just didn't get far enough away to say that these are the same. Because if they were this far away but not far away enough to reject, this is still evidence against the thought that they're the same, right? Okay, so it doesn't mean if I don't reject the null hypothesis, it doesn't mean that the null is true. Okay, so I'll come back to this thought again. We never conclude things in the null hypothesis. We never prove statements that are given in the null hypothesis. We can disprove them, but we can't prove them. So, in hypothesis testing, there are some important errors that could be made. And some of the board exam questions you see may involve these types of errors. And so understanding where they come from and how they fit into hypothesis testing is important. So I've got this little table here, and the columns unfortunately represent things that we really in practice never know. And this is the true status of the null hypothesis. So this first column is that the null hypothesis is true. And the second column is that the null hypothesis is really false. Okay, again, we never really know this. What we're just looking for is evidence in favor of or against the null hypothesis. But what we do know is the result of our hypothesis test and the conclusion that could be reached. So this first conclusion is that we reject the null hypothesis. And the second is that we fail to reject the null hypothesis. So if we reject the null hypothesis and the null hypothesis is really false, are we doing a good thing? Reject the null hypothesis and the null hypothesis is false. You bet. That's the right decision. Likewise, if we fail to reject the null hypothesis and something we'll never know, the null hypothesis is really in fact true, then we're reaching the right conclusion. We've made the right decision with our hypothesis test. So now we've got a couple of other things that could happen here. I could reject the null hypothesis when the null hypothesis is in fact true. Anybody know what that's called? It's my type 1 error. Very good. The type 1 error, rejecting the null hypothesis when the null hypothesis is really true. That's something that we don't want to do in our statistical test. And in fact, we don't want to make this error so bad that we set the probability of making that error before we even carry out the statistics test. How many of you have heard of the magical 0.05? Right? So 0.05 is this probability of making a type 1 error. It's what we call alpha. We usually compare a p-value from the test to this alpha level. And if the p-value is smaller than this, then we reject the null hypothesis. But this type 1 error is something that we often try to control from the outset of this study. We want to make sure the probability of making that error is pretty small. Okay, and then we have another error. What if we fail to reject the null hypothesis when the null hypothesis is false? Because statisticians lack creativity, we call this the type 2 error. I think we really missed an opportunity to get interesting with these names. But this is the probability of failing to reject the null hypothesis and when the null hypothesis is really false. Right? We often call that beta. And another important term that comes up with hypothesis testing is the power of the test. The power of the test has an interesting relationship with the probability of a type 2 error, or beta. They're inverses of each other. So the power of the test is defined as the probability of rejecting the null hypothesis when it's really false. That's what we want to do. We want to be able to detect this difference because they're not the same. So what's the power that we have to detect that? Well, we can find that by computing 1 minus the probability of the type 2 error. Now, I don't think you're going to be asked to compute these probabilities on your board exams, but understanding where they come from and how these errors can be made is important. So, we only make a type 1 error when we reject the null hypothesis. Now, we're either making the right decision or it's possible that we're making a type 1 error. Likewise, when we fail to reject the null hypothesis, we're either making the right decision or we're making a type 2 error. So those are the overall concepts that I think are important takeaways from this slide. Okay, in a randomized clinical trial, 2 urine collection methods, A and B, were used to see if the urine contamination rates differ between 2 groups of children. B had a significantly higher contamination rate than A. Okay, so we carried out a statistical test. We concluded that B had a significantly higher contamination rate than A. And our question is, what error is possible in this conclusion? Type 1 error, because the null's rejected. Type 2 error, since the null's rejected. Type 1 error, since we failed to reject the null. Type 2 error, since we failed to reject the null. Or no error, since there was a significant conclusion. All right, so take a second and answer that. Okay, yeah, so whenever we reject the null hypothesis, as we stated before, we're either making the right decision or we're making a type 1 error. All right, so just kind of link reject the null hypothesis with type 1 error, fail to reject the null hypothesis with type 2 error. Some people selected E, no error since findings are significant. You know, unfortunately, in the world of statistics, we can reach the wrong conclusion sometimes. Even if the data support the hypotheses that we're trying to test, there's still some uncertainty associated with our conclusion. And I know that that's sort of like pulling back the curtain and revealing dark secrets about the world of statistics, but there is a lot of uncertainty associated with these hypothesis tests. And it isn't until you start looking at things like Bayesian types of statistics that you can associate probabilities with the conclusions that you're making from these hypothesis tests. So unfortunately, we lead people to believe that we get this really nice yes-no conclusion, and that's the way it is. But the truth is that sometimes we'll come up with a wrong conclusion, even when the findings are significant. Okay, so a p-value. How many of you have heard this term before? Come across it in a journal? Okay, so it's all over the place. And a p-value is simply a probability, but it's important how we define this probability. It's the probability of observing the data from a particular study if, so there's a conditional statement there, if the null hypothesis is true. Okay, so think about a null hypothesis for treatment A and B. We got treatment A and B here. The null hypothesis says that they're the same. And what I observed in my data was actually this. Now I'm computing a probability of observing this if this is really the case. Right? So the definition is the probability of observing the data if the null hypothesis is really true. So what would you suspect if that probability is really small? The probability that we obtained the data we saw if the null hypothesis is true. What does that tell you about the null hypothesis? Is that evidence in favor of or against? That would be evidence against the null hypothesis. Okay. Null hypothesis says we're here, we observe something here. The p-value is really small. So that means I don't think, from what I saw, I'm seeing this, I don't think this is really the case. So that p-value, if it's small enough, less than that 0.05, less than the probability of our type 1 error, or alpha, is considered statistically significant. So think about this. A lot of people get connected to this 0.05, and it just becomes sort of this magic threshold. Anything less than 0.05 is absolutely significant. Anything above 0.05 isn't. But 0.05 is really just a probability. It's saying that if the null hypothesis is true, we observed something that happens 1 out of 20 times. 1 time in 20. And through the years, people have said, well, we don't feel like we're quite that lucky that we would just observe this the time that we did our experiment and we observed this kind of difference. So that's probably enough evidence against the null hypothesis to say that it's false. And then even smaller p-values, 0.01 would be something that happens 1 in 100 times. So I think it's helpful to think about that p-value in terms of the 1 out of 20 or the 1 in 100 times rather than just sort of this comparing it to this magic threshold of 0.05. Confidence intervals represent just plausible values that the real treatment group difference could assume, or if we're talking about odds ratios or risk ratios, that those ratios could assume. So, unfortunately, when I compute an odds ratio from a sample of people, what I'm trying to do is make a statement about that from the sample to a much larger population. And I know that that estimate from the sample is going to be wrong. It's not going to be equal to the estimate from the population. But hopefully it's close. And so I'll make some interval around there that's likely to contain the true estimate of the population. The true estimate of the group that I'm trying to make statements about. So that's where this confidence interval comes from. It contains these plausible values, right? And like I said, this could be for group differences or for odds or relative risk ratios. If a 95% confidence interval contains 0 for a treatment difference, then it is not significant. That tells me that group A and group B, the difference between the means may be 0. They may overlap. Right? So if my interval contains 0, then they're not significantly different. Likewise, for an odds ratio or relative risk, if that interval contains what? 1, then they're not significantly different. Right? So as you encounter questions like this on the board, on your board exams, be very careful. Are they talking about differences between groups, or are they talking about ratios between groups? And then you'll know the number that you're looking for in that confidence interval. For an example, a meta-analysis is done to see if blood glucose monitoring leads to lower hemoglobin A1C levels. The differences, and I've taken monitored minus not monitored, in hemoglobin A1C along with 95% confidence intervals are given here. So this is the estimate of the difference, and here is the 95% confidence interval, ranging from negative 1.25 to 1. Here is the estimate of another difference from another study and its corresponding confidence interval. And I have that for those 4 studies. So, what is the most accurate conclusion about this particular study? Blood glucose monitoring has a small statistically significant improvement on HbA1c. Blood glucose monitoring leads to a small statistically significant worsening of HbA1c. Blood glucose monitoring leads to a moderate statistically significant improvement in HbA1c. Or the monitoring is not associated with a statistically significant change in HbA1c. Okay, so yeah, 81% of you got the right answer. Those confidence intervals all contained 0, so there was no significant difference between those that were monitored and those that weren't monitored in terms of their blood glucose, their HbA1cs. That's just a graphic of that meta-analysis. Okay, so I think that I've got just a couple more slides here. We'll look at another meta-analysis performed to look at whether breastfeeding reduces the risk of developing breast cancer. We have 6 studies in this meta-analysis. We looked at the odds ratio with non-breastfeeding women as the reference group. Okay, so you have to think back to the odds ratio. Non-breastfeeding women are in the denominator. Odds for breastfeeding women are in the numerator. And here are the confidence intervals. So you can take a moment to provide an answer to the most appropriate conclusion there. And right away we saw in those intervals that they contained which important number? 1. So we know that there was no significant difference between the breastfeeding and non-breastfeeding mothers in terms of their risk for cancer. Okay, so number needed to treat is an important term in helping you identify the efficacy of a drug. Okay, and it's actually got a very simple calculation. So the number needed to treat is just 1 over what we call the absolute risk difference. And I'll define each of these things. So it's 1 over the proportion of bad outcomes among the controls minus the proportion of bad outcomes among the treatment. So this pi control is that proportion among the controls, and this pi treatment is that proportion of bad outcomes among the treatment group. So the absolute risk reduction is just the difference between those proportions. Okay, so maybe 30% of my subjects in the control group had this bad outcome, and 5% in my treatment group had this bad outcome. So my absolute risk reduction there is 25%. And my number needed to treat then is going to be 1 over 0.25. Right? So it's a very simple calculation and very easy to do, especially in a shorter period of time on your board exams. So a couple of points of interest about the number needed to treat. Think about that number in the denominator. It's the difference between proportions. So what's the possible range of values for the NNT? If I take 2 proportions and look at the difference between them, can I get something larger than 1? That's not going to be possible. If in an extreme situation, if my proportion of bad outcomes among the controls, all of them had that bad outcome, and in my treatment, none of them had that bad outcome, the largest that denominator could be is what? Just one, right? So in sort of that extreme situation, the number needed to treat then would be 1. And that meant that the treatment was really good compared to the control. The proportion of bad outcomes among the treatment was nothing, and the proportion of bad outcomes among the controls was everybody, right? So it's bounded below by 1. What about the other side? How large could that get? What if the proportion of bad outcomes among the treatments is really close to the proportion of bad outcomes among the controls? That difference in the denominator could be really small. So what happens to that number? It gets really, really large. The number needed to treat gets really large. And so this is an important point. If the number needed to treat is small, that tells you that the treatment is very effective relative to the control against guarding against that bad outcome. Fewer people need to take this treatment in order to avoid a bad outcome. What if we get a negative? So what if we have a large NNT? Well, the opposite is true. If the NNT is really large, then it's not that much better. The treatment is not that much better in guarding against this adverse outcome than the control, because those proportions are going to be really close. Right? So we want the NNT to be small. What does a negative NNT mean? The proportion of bad outcomes among the treatment group was actually higher than the proportion of bad outcomes among the control. So we don't typically report negative NNTs. Anybody know what we call those? We call that number needed to harm. Right? So the treatment is actually doing worse than the control. So last little question here. A study's done to test a new drug for status asthmaticus. Patients receive the standard treatment plus the new drug, or standard treatment plus a placebo. After a 4-year follow-up, 30 out of 100 subjects receiving the placebo died, while 10 out of 100 receiving the new drug died. What is the number needed to treat with the new drug in order to prevent one death? Okay, so I'll give you guys a moment to do that calculation. Again, this is not a fair one. 10 seconds. Good. So 86% of you got that right in a very short period of time. I'm impressed. So the way that we could work that out is just sketching out on a little sheet of paper here. 30 out of 100 minus 10 out of 100 gives you 20 out of 100 in the denominator. And then we can invert that and get 100 out of 20, 100 over 20 equal to 5. So just something to note, the absolute risk reduction is 20%, that value in the denominator, and that has a direct interpretation. That means that the new drug reduces the risk of mortality by 20%. In this kind of situation, we need to treat 5 people over 4 years with the new drug to prevent one bad outcome. And as I mentioned earlier, we want that number needed to treat. The smaller that number is, the better the treatment is. Okay, thank you. Good luck on your exams.